Welcome everyone to Digitalized in Stockholm 2022, and within that to the presentation of the project DEMOCRITUS, Decision Making in Critical Societal Infrastructures. In this project we would like to see how can we, with the help of digitalization, monitor, control and maintain large-scale infrastructures from our everyday life, like roads and build infrastructure, networks, communication and computing infrastructure, utilities like water distribution, heating and electricity, and well, all emerging large-scale applications that you can imagine. I'm Victoria Fodor, I'm professor in communication networks at KTH, and here you can see the other partners in the project from RISE, KTH and Stockholm University. So let's see what are the scientific challenges that we have to address for this large-scale monitoring and control. First of all, the sense data in these infrastructures is distributed over a large geographic area. Therefore, we need new learning methods that are designed to work over large-scale distributed data sets. This data and also the control actions needs to be collected and then distributed. So we need network support. Now, these networking applications are very different from the applications that we have today, and therefore we need new network design solutions. Well, third, here we would like to address the needs of real physical systems. And to do so, we have to find new ways of modeling these systems, ways that can work together with all these database solutions that we would like to design. And finally, we have to find solutions to evaluate our systems. Clearly, we cannot build experimental systems because we are talking about large-scale infrastructures here. So we have to find integrated environments that can evaluate both the communication, the learning, and the infrastructure in the same system. So let's start with learning and network design. And specifically with networking for learning. Let's see what is the scenario that we have here. Right, we have these large-scale infrastructures. Here I have an example for an electrical grid. Data from this infrastructure has to be considered for learning. This data has to be collected efficiently, or the learning and the actuation has to be distributed. And this is what we can see nowadays in the emerging edge computing solutions, where computing is not only implemented in a centralized cloud, but also at the edge of the network. Finally, these learning applications have some specific properties. And an important one is that, well, not only that the data that we collect does not need to be fully correct, but also that often we don't need an individual information from, let's say, from all the end users or the measurement units, but we need some kind of function of this information. For example, the sum of the gradients of the local learning processes. So this means that we have a new networking scenario, and let's see what are the questions that we try to address in this project. Well, the first one is the question of dimensioning. Learning over networks requires both communication and computing resources. Therefore, we need new dimensioning techniques that consider both. Second, as mentioned, often we don't need the individual data, but a function of that, for example, a simple sum. This means that the orthogonal transmission that we usually use in wireless networks, that is, all the users get its separate resource to transmit, this orthogonal transmission is inefficient. It's a waste of resources in the case of learning. So specifically in this project, we have shown that small cells that work very well for, if you consider only the efficiency of communication, may not be preferable when we consider learning, because the computing resources will be distributed and has to be overdimensioned. Second, we propose new physical layer techniques and also solutions to achieve reliability for so-called channel computing when operations over input data is done over the wireless channel with the idea that the users should transmit at the same time and the computation therefore happens over the air. Let's see, considering the challenges of learning, clearly we are trying to do this online learning often over resource constrained network environments. Therefore, we design novel feature reduction and measurement sampling techniques that can significantly reduce the amount of data that is collected, and with that, the training overhead of learning while maintaining the required prediction accuracy. We also evaluated these solutions over testbeds at KTH. Let's look at the next large topic, the modeling of the physical systems, specifically the water distribution networks. Why do we consider the water distribution network as our use case? We consider this because it's very important and it's also very challenging. Water distribution networks are often very old infrastructures. It has a very low level digitalization. These infrastructures are large scale and, well, we all know that it's very critical to get drinking water. At the same time, the water is becoming a scarce resource, while leakage is still using a high level of water loss. In Europe, we are talking about 10-20%, but this loss can reach 50% as well. And, well, contamination still happens. We notice that in Sweden once in a while as well, when people cannot drink tap water for days, and the source of this contamination is often very hard to find. So the challenges that we would like to address in this project is finding leaks in the distribution network and finding the source of contamination. So looking at the problem of finding the source of water leakage, we have a large amount of data in today's networks that actually could be used for this localization. This data is often collected at the end devices, right? We know, for example, the water consumption, or we may know the water consumption at the end users. So the question is, how can we use this data that is collected at the endpoints of a water distribution network to localize leaks, which means we have to find the pipe with the leak and, well, the leak itself, the location of the leak on that pipe. In this project, we are designing data and model-based solutions to do so, and we propose solutions to find both the pipe and the location with very high accuracy from data at the endpoint, considering water consumption and pressure measurements. Now let's look at the tracking of pollution in these water distribution networks. To do so, what we assume is that we have sensor measurements in the water distribution network, and from these measurements we would like to predict how the contamination will spread in the network. Then these prediction methods can then be used also for backtracking and finding the source of contamination. For this work, we are using large-scale water distribution network emulators. We are using the one that is called APANET and is used in the water industry. These simulators are detailed simulators that describe the water flow in the network, in the water distribution network, based on millions of parameters of this distribution network. So in this project, we use this APANET data to build then mathematical models that then can be learned for learning and prediction. And specifically, we propose tracking and backtracking based on ensemble Markov models. And finally, let's talk a little bit about this emulation simulation environment that we need to build up to support our research, and specifically the case of the monitoring and control of water distribution networks. So as said, we are using this APANET water network simulation, and we connect this simulator with units for analysis, estimation, decision making. And also we connect the simulator with demand modeling and leakage modeling that we built up. So the challenge of this way of using the APANET simulator that we have to note is that these detailed simulators consider an input, and then based on this input simulate what would happen in a real network. Now, what we have a problem at hand for us is actually the opposite. We have a given output, the sensor measurements, and from that we would like to find the input to the system, for example, where the contamination entered the network. So with that, I summarized the main research activities that we have in the DEMOCRITUS project. If you are interested in further details, here you can see a set of our selected publications in all these different areas, from networking, learning, up to modeling the water networks for leakage and contamination tracking. Thank you again for listening.